All right, so next up, we need to talk about balancing equations. Balancing equations can be really tricky for a lot of students. However, it's just important to understand the fundamental principle as to why do I balance an equation in the first place. And that whole idea dates back to a particular law. So when I'm talking about balancing equations, we always need to think about our law of conservation of mass. So with our law of conservation of mass, mass cannot be formed or destroyed. Now, by mass, of course, we are talking about matter. We can't create matter or destroy matter. To do so, we need to be some sort of god. Rather, we can change its form, we can change its state, but I can't somehow end up with more matter than I started with. So when I look at balancing an equation, I need to make sure that I am not gaining or losing any particular atoms. So keep this in mind at all times. This is law conservation of matter. So when I'm thinking about this, I see a sodium, I see 2 chlorine atoms. But when I look over here, I only have 1 chlorine atom. That to me says that somehow chlorine got destroyed. That can't happen. We've said that will not happen, cannot be done. So I need to think that I need to have 2 chlorines over here. So we add this value here, and we call it a coefficient. Think about it in math. Numerical coefficients we use when dealing with polynomials or dealing with complex algebra. Same idea here. So I need to have 2 NaCl's on the backside here to make sure that the right amount of chlorine exists. But I have somehow now created matter. I now have 2 NAs. That's not possible either. So I need to start with 2 there. What this equation now says is that for it to happen, there needs to be 2 sodiums, 1 molecule of chlorine gas, and you will get 2 molecules of sodium chloride out the other side. This does not violate the law of conservation of mass because we have the same amount of matter going in as coming out. A way to check it is to just count up everything on the side. I have Na, Na, Cl, Cl because of the 2, and I have NaCl, NaCl, and I can just count it up 1, 2, 1, 2, 1, 2, 1, 2. Good. Everything is hunky-dory. We haven't lost any matter along the way. However, these can get really confusing in a big hurry. So let's look at one where we start to get complex charges. A great example of this are rusting equations. So we could look at something like iron reacting with oxygen. This leads to Fe2O3. This is complicated because ionic bonds sometimes have strange natures of their charges. We talked about this in naming ionic bonds. The charges of metals can be really tricky sometimes. So the first thing you might say is, I have 2 irons. And you would be right. So let's start there. Let's think about it. 2 irons. Then I have 3 oxygens. Well, my oxygen is a diatomic. It needs to exist in groups of 2. You can't put a group of 2 into 3. So you kind of reach an impasse here. This is where a math skill comes hugely in handy. If I have an odd number, I just have to multiply it by 2 to become an even number. So now I have 6 oxygens. Well, that I can work with. That I can multiply over here and get 6 oxygens. But my iron has been affected. I now have 2 groups of 2. Well, now I have 4 irons. 2 times 2. So I need to up this to 4. And now I have a completed equation. The way I check this, I go Fe, 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 4 irons, 3 groups of O2, so I get O2, 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 or 6O, right? 4Fe. Now over here I've got 2 groups of Fe2, O3, Fe2, O3, 1, 2, 3, 4, 4 Fe's, 3, 6, 6, O. Perfect. Everything balances out exactly the way I would like it to. So for that purpose, balancing proves the law of conservation of mass. However, it can be very difficult, so I highly advise doing extra practice on all balancing equations because you don't want to get bamboozled on some sort of exam. All right, the next thing we're going to talk about is naming ionic and molecular compounds.